Dr. John Abraham is a climate researcher at the University of St. Thomas. Much of his research focuses on the world's oceans, and his research team has measured how fast the oceans are warming and what the consequences will be in the future. He also co-founded a company that uses sunlight to make drinking water in the developing world. In addition, he writes about climate change in The Guardian, and he is here to let us know what is happening to the climate, how fast it's changing, and what can be done about it. So please join me in welcoming Dr. John Abraham.
Thanks. It's a real pleasure to talk with you all today. I'm going to keep my comments to about 30 minutes. I want to encourage questions to be asked. I should be agile enough to answer questions on the fly as long as you use the chat option or verbally state your questions. But it's a pleasure to be on this call today. And I'm just going to get right into it because I know that time is somewhat short. So I will share my screen. I think you can see my screen now. And if people, this is a shortened version of a talk that I give pretty frequently. If anyone wants these slides or any of the data behind these slides, feel free to just let me know, ask, and I'll be happy to provide them. All right, so what's happening with the climate? So I'm a climate scientist, but I'm also an engineer who works on solutions to the climate problem. And I believe that these solutions have to be integrally tied to what's actually happening in the climate. We want to make good decisions so that our decisions will actually have a positive output on the climate. So I want to walk through some of the things that we know. These are undisputed facts. We know that the Earth is warming. That's unequivocal. We know that at each of the last 5 decades was warmer than the prior decade. We know extreme weather is increasing. We know that Antarctica and Greenland are losing ice. We know there's decreased snow cover. Sea levels are rising. I know you guys love to read, right? You're like, oh my God, this is going to be bullet point after bullet point. Don't worry, I've got some fancy images too. We know the poles are warming faster than other regions. We're losing glacier ice, and the oceans are becoming more acidic. And that last one is one that I'm going to spend just a moment on. If you have a soda stream at home, or if you buy sodas, those are called carbonated beverages. The reason why they're spicy and bubbly is because they have carbon dioxide dissolved in them. We are actually putting so much carbon dioxide into the atmosphere that it's dissolving into the ocean waters and making it more like soda, less like ocean water. So that's the acidic issue at the bottom. Anyways, you're looking at some undisputed facts. Now, the vast majority of climate scientists say that these things are connected. They are all related to each other. There are an extraordinarily small minority of climate scientists. I don't know, it's very hard to find any these days that think these issues are unrelated. But if you turn on cable news or if you go to Facebook, you might find people who don't understand that these items are related to each other. Now, I want to show you the climate change through the lens of a scientist. We don't just look at what's happening. We want to understand patterns, and we call these fingerprints. It's not just that the Earth is warming. It's that it's warming in the right way to implicate humans. There's a lot of reasons why the Earth might warm. The sun could get hotter. There could be decreased cloud cover. There could be the tilt of the Earth might change a little bit. All kinds of things can warm the planet. Why do we know that this warming is caused by humans? It's because it's warming in the right way. I'm going to give you a few examples. More at night than during the day. That is, it's warming more when the sun isn't shining. If the sun was getting hotter and that was the cause of climate change, then the daytimes would be warming faster than night times. But that's not what we're observing. We're observing the nights warming faster than days. As another example, we're observing winter warming faster than summer, as you can see in the lower left part of this screen. One more example, the upper atmosphere is getting colder because we're holding the heat down just like an extra blanket. So all of these patterns that we're seeing are consistent with increased greenhouse gases. They are not consistent with natural explanations of climate change. And this slide shows why scientists are so convinced that climate change is human caused. Now you're looking at a graph. This is one of the most famous graphs of all time. This is called the Keeling curve, named after Charles David Keeling. And there's a red line that goes up and down, up and down, up and down in a sawtooth pattern. That is the amount of carbon dioxide that's been in the atmosphere. Now, if you look at the bottom of this graph, you'll see that the measurements were made starting in the late 50s. And the measurements continue today. This graph, which is a continuous measurement of carbon dioxide in the atmosphere, shows unequivocal changes to the atmosphere. And this is due to humans. This increasing red line is totally due to humans. There's no dispute. Humans are increasing greenhouse gases. It's not just carbon dioxide. There's other greenhouse gases. This is a graph that starts at year 0, which is actually 2,000 years ago, and ends in the year 2000. And you see 3 important greenhouse gases: carbon dioxide in red, methane in blue, and nitrous oxide in black. All of those greenhouse gases were more or less constant until the Industrial Revolution in the 1800s, and then they all began to rise. Now, you'll hear me talk more about carbon dioxide than the other greenhouse gases, and that's because carbon dioxide is the most important human-emitted greenhouse gas. But I want you to know that there are other greenhouse gases that matter as well. So what, John? So what? Greenhouse gases are going up. That's great. Why do we care? Well, we care because it changes the climate. What you see on the screen here, and by the way, is I've got my my tile of your faces on my screen. If that's impeding your vision, let me know. Okay, I don't think it is. Okay, so what I'm going to show you, this is data from NASA, and every black dot is the temperature of the Earth for a particular year. And you'll notice that some years the temperature goes up a little bit, some years it goes down. It's got this jagged kind of behavior. We want to look at the long-term trends, which are shown by the red curve. And I'm going to show you the hottest years ever recorded by humans. Hottest ever. Every hot year, the hottest, how many do I have? The hottest 14 years have all occurred since the year 2000. This isn't just happenstance. It's not, if the Earth's climate was naturally evolving, you wouldn't see a pattern like this. So the reason why we care so much about greenhouse gases is because what it does to the Earth's temperature and other aspects. Now, you heard mention that I was a climate scientist and I do work mainly in oceans. And my team measures how fast the oceans are warming. Let me explain why that's so important. 93% of global warming heat ends up in the oceans. So if you want to understand how fast the Earth is warming, you must measure the oceans. Can these screenshots be included in our minutes? Jackie, I will provide these, the slides, and you guys can do whatever you want with them. Absolutely, I'll be happy to provide these. What my research has shown, and it wasn't just me, it was an international team, is that the oceans are warming at an ever faster rate, and the amount of heat going into the oceans is equivalent to 5 Hiroshima bombs exploding every second of every minute of every hour of every day of every week for the entire year. 5 Hiroshima bombs worth of energy are going off in our oceans. And this research was covered by CNN. It was also covered by the Telegraph. Even Fox News covered this study, which was a pretty shocking study. So this, the reason I show you this is because it helps put in context the research that I do on climate. We can go back further in time, though. We can go back hundreds of thousands of years to tell what the Earth's climate looked like. Now, this is a a graph, and my wife always tells me every single graph that you put on your presentation makes half the people fall asleep. Now, that's not true with this group because you guys are technically attuned, but I do promise there won't be that many more graphs. This is a graph that on the left, I don't know if you can see my cursor, but it's up. On the left, we have a 400. That's 400,000 years ago. And on the right, there's a 0. That's today. And there are two colored curves, red and green. Red is temperature. Green is greenhouse gases. And what I want you to notice is they go together. We call them handcuffed together. Whenever one moves, the other one moves. So temperature and greenhouse gases are integrally connected to each other. And anyone telling you that greenhouse gases can go up without temperature going up is defying hundreds of thousands of years of experience that we have with our planet. So let's look into the future. What do we expect and what are some of the consequences going to be? This is a graph that shows temperatures from the year 1000 to the year 2000. And the red stuff on the right, those are actual thermometer temperature measurements that we've been making since the early 1900s. But we're concerned about this small temperature rise that we've experienced. That's what's going to happen by the year 2100. So as you think about heat waves and ocean levels rising, what we're seeing now is just literally the tip of the iceberg. Stephen has asked a great question. How do you measure, assess temperatures from 400,000 years ago? Great question, Stephen. And this is a slide I usually have in my presentation when I have more time. We use what are called proxies from nature. And I'm going to explain a proxy. Let's say you go camping to northern Minnesota. And where everyone else is drinking beer and roasting marshmallows, you decide to dig into the ground for some reason. And you discover crocodile fossils and palm fronds in the earth. You would conclude that the climate a long time ago where at your campsite was warmer. That's a natural signal that tells us what the temperature was like. There are other natural signals. Ice cores are a natural signal. We can actually drill into ice cores and discover the temperature of the long past history. We can use sediments, pollen. As pollen falls, we can tell what plants were vibrant in certain areas. That tells us about climate. Tree rings will tell us about climate. Sediments under the ocean or lake waters tell us about climate. So even before we had thermometers, we did have a sense of what was happening with the climate. That's a great question. So what are the impacts in the US? This was an image that I got just yesterday, I think. This is the US Drought Monitor. You can go look up the US Drought Monitor right now and get the map of how our country looks. And you'll notice the darker red and orange places are under severe to exceptional drought. And I don't care what year you look at this data, we are experiencing more frequent and more damaging droughts. And these have economic consequences. I mean, climate change is about polar bears, but it's also about dollars and cents, and it's about the economy. And the consequences of climate change are very, very expensive. We had a drought in the year 2012 in the US that cost us $35 billion. That's with a B. We had a recent drought in California that cost just California $4 billion in lost agricultural productivity. So when we talk about climate change, we are talking about social, biological, and economic consequences. The drought pattern that you see on my screen has economic consequences to us, even in Minnesota. But not only is drought changing, rainfall is changing. Now, as you know, the warmer it is, the more storms you can have because of humidity. If I were to ask you, is it more humid in January or July, you would immediately say July. And that's when we get heavy rainstorms. As the earth warms, there's more moisture in the atmosphere, and that means that we can get heavier downpours. So we have this weird situation where the earth is warming and getting drier in some areas, but it's getting wetter in other areas. And the general rule of thumb is this: If you live in an area that's currently wet, you're going to become wetter. If you live in an area that's currently dry, you will become drier, and your rains will come in heavier downbursts. So what you are looking at is a map of the US, and we've tracked the 99th percentile precipitation events. Think of that as the 1% most heavy rainfalls. These are the rainfalls that cause the worst damage, the worst floods. Those rainfalls have increased 55% in the northeast part of the US. They've increased 42% in the central part of the US. So heavy, heavy downpours that lead to floods are increasing as well. I'm showing you a map of ocean waters near the Gulf of Mexico. You can see the US, Central America, South America, Mexico in black, and the colors are ocean temperatures. Anything that is orange or yellow or red is warmer than it should be, warmer than average. Now, why would I show you temperatures of oceans from October 8th, 2018? Because this was happening that day. We had a number of hurricanes that occurred that summer. One of them was a near miss of New Orleans. But I'm showing you satellite images of before and after these hurricanes passed over the southeast US. So another consequence is warmer waters in a warmer planet gives us bigger, more intense storms. And these have economic consequences as well. How much does climate change cost us? Well, I am showing you, and this is from NOAA, National Oceanic and Atmospheric Administration, the cost of climate-related events. Now, this is a weird graph because on the left-hand side, it has the number of events that cost $1 billion or more. I want you to look at the right-hand side, which is the actual cost. 2020, climate change cost us almost $400 billion. And over the last decade or so, it's averaged over $200 billion. And the costs are going up. And these are costs that are already adjusted for inflation. These costs to our country are borne by us all, and they are reflected around the world with other countries. If someone doesn't care about polar bears or about natural wildlife, and all they care about is money, this is the graph that should motivate them to take action on climate change. If we spent a fraction of these costs on dealing with climate change, we would be in a much better situation. I'm going to show a couple other images. Most of these will be photographs. I'm going to focus some attention on the ice sheets of our planet. We have two large ice sheets on our planet. One covers Greenland and one covers Antarctica. Those ice sheets are important because they're melting, and they have the amount of water that can raise the oceans by many feet. On the right-hand image is a photograph of a river of water, which I hope you can see. That's called a moulin. These rivers of water form on Greenland, and they flow through crevices in the ice and then into the ocean, and they're accelerating the ice loss from Greenland. Greenland itself, if Greenland were to melt just itself, you would get 7 meters of sea level rise, which is about 24 feet. This is a lake. Well, it looks like a lake, but in the distance, you can see a white zone. That is an ice sheet. This is a lake on top of an ice sheet. And that is you see a motorboat of someone going across a lake on an ice sheet. Let's turn our attention to the south. I've highlighted the Larsen B Ice Shelf. Now, Antarctica, which is at the South Pole, has the left-hand side, which is the West Antarctica, and the east side, which is the right-hand side. Scientists are most concerned about West Antarctica because it is unstable. West Antarctica has enough ice to raise ocean levels by 5 meters or about 17 feet. But let's look at just one example of an ice sheet. I'm going to show you a series of photographs. This one is January 31st, 2002. If you look closely, you can see some black dots. Those are melt ponds. And then a series of satellite photographs over a month and a half showed the utter collapse of this ice shelf into the water. This stunned scientists. This ice sheet had been around for tens of thousands of years, and it was the size of Rhode Island. Fell into the ocean in a month and a half. This is a satellite photograph of the Wilkins Ice Shelf, which collapsed in 2009, and other ice shelves. In fact, a story just came out yesterday, a new study just came out yesterday in, I believe, Nature, showing that we are losing ice faster from Antarctica than we had anticipated. Here's some photographs of the Mccarty Glacier in Alaska. One photograph was 1909, the next one is 2004, and the camera is in the exact same location. Glaciers are being lost around the world. Here's another before and after photograph of the Muir and Riggs glaciers, 2004 compared to 1941. I'm going to just give a couple more satellite photographs. This one is on an island off of Antarctica. And now this is amazing. This is from 2020, so just 2 years ago. The left-hand photograph shows an ice-covered island on February 4th. Look at what happened in 9 days. A large part of the island had ice that melted, and there were melt ponds that had formed. Temperatures reached, now I want to remind you, this is Antarctica. Temperatures reached 65 Fahrenheit. Stunning change of climate. Why do we care about ice loss? Because as ice melts and flows into the ocean, sea levels rise. I've got two topological maps showing how high different regions are above sea level. The left-hand side is Asia in general, or Southeast Asia in general. The right-hand side is focused on Bangladesh. 20 million people within Bangladesh alone will be displaced by rising sea level by the year 2100. 20 million people. If you are the government in India, what do you do about 20 million climate refugees on your border? Worldwide, about 150 million people live within a meter of sea level. About a meter of sea level rise is what we expect to occur by the year 2100. So what do we do? There is, I think this is my last graph, so I can say that. This is a graph that shows increase of carbon in the atmosphere projected out to 2050. We want to bring this curve down, and there's no silver bullet. There's no space aliens or magic pixie dust that's going to save us. But what can save us is silver buckshot. A lot of things that we do together add up to bring this emissions down. And that's really how we have to think about handling the climate change problem. We need all hands on deck, and we need to do many things simultaneously. I'm actually cautiously optimistic as a climate scientist, and it's because of this complicated graph or table. This table shows the cost of energy sources. And the upper part is fossil fuels, the lower part is green energy. The LCOE stands for levelized cost of, I think, employment. I think that's what E is. Compare the costs in red with wind and solar. Wind and solar costs have dropped so dramatically that now you can power your homes and your buildings cheaper than you could with fossil fuels. I'll just use myself as an example. I have solar panels on my house. I drive an electric car. I don't pay gas at all. I literally drive by sunlight. And when gas goes to $4 a gallon or $5 a gallon, it doesn't bother me at all. I'm saving money and saving the environment at the same time. So now we're in a position where you can save the environment and make sound economic choices all at the same time. Change is possible. I love the photograph on the left is a rusty oil well in Texas with beautiful wind turbines beyond it. The right-hand image is a entrepreneur who's making algae biofuels to power vehicles, sucking carbon dioxide out of the atmosphere into a biofuel that then you can run a car with. Change is happening. We just need to speed it up. I'm going to end with 4 points, just 4 things I want you to remember because I've gone through a lot already. Point number 1, we know the climate's changing. We've actually known it for over 150 years. Al Gore didn't invent climate change. The first studies on climate change were done in the 1800s. The first climate prediction was 1896. We've known this for a long time. Fortunately, we can solve this problem. We can solve it with today's technology. Thank you, Hobart. Levelized cost of energy was LCOE, so thanks for that. We can solve this problem today with today's technology. We don't need to wait any longer. We can implement viable decisions now that can make our world better. The third point that I want you to remember is we're at a point where we can simultaneously help the environment, create jobs. I mean, wind and solar jobs are going through the roof, even here in Minnesota. I would rather pay a farmer for wind power or a startup company in Minneapolis for solar panels than sending fleets to protect oil routes near countries that don't like us so much. I mean, we can save the environment and create jobs here in Minnesota and become an exporter. We can also improve our national security. And the last point I want to make is some people say it's too expensive to take action on climate change. I say it's too expensive to do nothing. Doing nothing is a choice. It's a choice with tremendous consequences. And we're at a point now where the choices to save the environment are also the choices that can help us save money. And that's the main reason I'm optimistic. I think that's my last slide. So I'm going to stop sharing and see if people have questions, maybe start a conversation.
Hey, John, I got a question for you.
All right,
Peter. Thank you so much for the presentation. So I joined a little late, but I don't know if you touched on ocean acidification and how that would affect ocean life, and maybe you could comment on that.
Peter, that's a great question. I did mention ocean acidification, but I didn't mention its impact. So what happens with ocean acidification is we're changing what's called the pH of the ocean. And that is a threat to animals that make carbon-based shells. So animals, small animals that are at the base of the food chain are suffering with the change of pH. It's actually the thing I'm most worried about because the oceans are central to food production around the world. But ocean acidification is harmful. Ocean acidification affects different animals in different ways. Some animals it doesn't affect much, but some it does affect a lot. The ones it affects are at the base of the food chain. So it's a big concern.
Okay, so where would you start? I mean, if you're going to go and like talk to people, and I'm thinking government officials, where would you start?
Yeah, great question. So strategically, we need to do 2 things. We need to adapt and mitigate. Mitigate refers to trying to slow down climate change. And we're really beyond, we're way beyond the point where we can stop climate change, way beyond. But by taking action and reducing our emissions, we could turn a worst case scenario into a scenario that is manageable. So we definitely need to reduce emissions. And the way to start is use energy more wisely. I mean, a gallon of gas, no one makes it. It was made by bacteria over millions of years. But a gallon of gas is actually magic. It's got so much energy. It can take an SUV, push it 60 miles an hour for 20 miles. That's freaking amazing. We shouldn't waste that. We should use that energy in the most conservative, efficient way possible. We shouldn't be wasting our energy heating and cooling houses that are very energy inefficient. Insulate your houses that'll drop your energy use. So I'm just trying to give a few examples of how we can we can lower our own personal emissions. But we also need to adapt, and that means to make our societies more robust. So there are some, well, I'll give you an example. The bill that, the big bill that went through with Manchin and Sinema finally agreeing to sign the bill, Sinema got drought relief for Arizona. And what that means is money, I think it was either $4 or $14 billion to make Arizona more drought resistant. So we are spending money, 4 million, thanks Hobart. We're spending money to try to reduce the impacts of climate change. And that's what I mean by adapt to it. Superstorm Sandy cost us about $70 billion. New York had to harden its electrical system and subway system. It had to spend money that it otherwise wouldn't have had to spend were it not for climate change. So we need to adapt and mitigate. Now, in terms of mitigation, we have to do it in 2 steps. We have to reduce our own personal energy use, and I'm sure people are already doing that. Maximize your energy draw from clean renewable sources. So let's say that you're an Xcel Energy customer, you can actually sign up for WindSource and you can power your house with wind energy. I did that for about 15 years before getting solar panels. So you can make these personal choices, but also you need to talk to your family and friends, and you need to let them know it matters to you. The people on this call are some of the smartest people on this topic. Your family and friends aren't as engaged as you are. They will listen. They should know this matters to you. Your elected officials should know it matters to you. I've been told that when one person calls an elected official's office, they're a crank. When 5 people call an elected official office, it's a groundswell. So make sure your elected officials understand that this matters to you. If for people who are resistant to taking action on climate change, I'm going to tell you what's happening internationally, because I do a lot of work around the world with green energy. China is killing us. China has a national policy. It's brilliant. They want to own the green energy market. The future economy is going to be driven by green energy. They want those jobs. When I go to Africa, I have to buy Chinese solar panels. When I go to South America, I'm buying Chinese products. I would love to export American products. It's green energy products, but right now that's very difficult. So for audiences who don't really care about polar bears or moose, they do care about jobs, and they do care about lost economic opportunities. And to the extent that the US is slow to maximize our green energy production, we will suffer economically because other countries are filling the void. And that was a really long-winded answer and terrible answer to your question, but I just had so much I wanted to get out. So my apologies.
Alrighty. And actually you answered 2 of my questions. So Tim, you got one?
Yeah. John, your slides are very much like Al Gore's. Same themes. It's kind of cool.
He copied me.
Yeah, but I had a question kind of related to the ocean.
Yeah.
It has this great thermal mass, and it takes forever for it to churn up, from the bottom to the top layers. And I'd always had the impression that even if we stopped emitting carbon dioxide and other gases today, it would take a long time to continue to warm. But lately, Al Gore's been saying, nope, once we reach net zero, a couple of years, it'll stop rising. What do you know?
Well, the answer is actually sort of in between. We are not going to emit, we're not going to get to net zero anytime soon. But net zero means that we emit as much energy, or we emit as much carbon dioxide as gets absorbed by the planet, so that there's no net increase. If we get to net zero, if we could get there today, we still have about 1.5 degrees Fahrenheit warming in the pipeline.
It's not as bad as I thought. Good.
Yeah. Well, I mean, it's about 70% of what's happened so far.
Yeah.
Now, if we don't reach, by the way, if that happens, I would be ecstatic. That means that our climate change problem will be something that's very manageable if we could do that. But of course, the worst case scenario is what we're most concerned with, And unfortunately, the worst case scenario is the business as usual scenario. So we definitely need to get to net zero. There will be some residual warming even if we get to net zero, but if we can get there, this world will be a much better place.
I have a question about the melting ice. It seems like that is irreversible. Is that true? And like, how big of a concern is that even if we stop emitting, if all the ice is melted?
Yeah.
It seems like an issue.
Yeah. And there's ice and there's ice. So sea ice, which is ice that floats in the ocean, that's much less of a concern than ice that's on land. The North Pole is water covered. So the ice that we've lost at the North Pole is already floating in the water, and as it melts, it won't really contribute that much to sea level rise. Although we have lost about 70% of the volume of ice in the Arctic. We've lost a ton of ice in the north. That's not the biggest issue with respect to sea level rise. The real big issues are Greenland and the Antarctica. And this is an issue that relates to what are called tipping points. Tipping points are, if we go far enough, we'll trigger some natural reaction that we then cannot stop and we're not in control. So one tipping point is melting permafrost with methane release. Once we melt enough permafrost that the methane release rises dramatically, we will then have lost control over the climate. Another tipping point is the ice sheets. Now with Greenland, the ice is melting from the edges, but also from the top down. And as you know, if you climb up to the top of a mountain, it gets colder, right? Well, as the level of ice falls, it is falling into warmer air. And so at some point, the top of the Greenland ice sheet will fall below the freezing location. And that's the tipping point we're worried about with Greenland. It absolutely can happen, and it may have already happened. Now, that's bad news. The good news is we can dramatically slow down how fast Greenland melts. I mean, Greenland could melt in 100 years or 1,000 years. And there's a huge difference in our ability to navigate that kind of process. West Antarctica is susceptible to tipping points as well, because West Antarctica has ice that is pinned to the top of little mountains. And Antarctica is melting from the bottom. It's actually melting because warm water is getting underneath it. It's melting it from the bottom up. And so there's a tipping point on West Antarctica as well, which we're concerned about. So there definitely are tipping points, but even if we cross a tipping point, we can still pull the brakes and slow the train long enough that we can take action. Now, action's not easy. Let me give you an example. Miami. If you know people in Miami, they will tell you that parts of Miami flood with high tide right now, or something called king tides. And that's going to get worse and worse and worse over time. Now, maybe you could build a wall. Let's build a wall around Miami. The problem is Miami's bedrock is porous, so the water just comes up from the ground. So Miami is a situation where, at least for the long-term prospects of that city, we've reached a tipping point because the oceans will rise and large parts of Miami will become flooded, and there's really nothing that we can do about it. But despite all that doom and gloom, despite the fact that there are tipping points that we have crossed or we might cross and we don't know when we're going to cross and all this, taking action, reducing emissions now, spending $1 to reduce emissions now will pay off more than $1 in future benefits. And what we really need to do is take our trajectory from this to this. Great question.
I've got another one.
All right.
So my dad was a World War II vet, and the thing he kind of talked to me or told me was how they converted from being a consumer economy to being a wartime economy. And that like they couldn't get gas and stuff like that, or as rationed. And I've started to use that analog for climate change, that we need to have a total conversion of industry, not unlike what was done for World War II. Would you
Yeah.
agree with that?
Yeah, I do. So I was actually looking up something while you were saying, okay, wartime economy. I love this World War II analogy because let me tell you what happened during World War II. The Allies produced, how many airplanes do you think were produced by the Allies? Don't even guess. I'm going to tell you, 640,000. 640,000 military planes were produced in 4 years. Holy smokes. If we did that with wind power, it's problem solved. Number of tanks and artillery vehicles, 4,400,000. Just the Allies in 4 years. So absolutely, we have it within us to solve this problem. And it's not the technical wherewithal, it's the, I don't know if you want to call it moral fortitude, intellectual fortitude, strategic thinking. We lack the will, we don't lack the means. But World War II is an excellent analogy. And if we had an all hands on deck approach, we could solve this problem extremely quickly.